Um, we'll continue from where we left last time. And last time we were looking at how we can construct new power series from all power series. And we did a very simple one where we started with this one over here, and we did that this is a geometric series. And using this one, we could find out 1 for x to the 5th over 1 minus x. So from last time, I'm not going to do the details again, but we did x to the 5th over 1 minus x. And that turned out to simply be, well, x to the k plus 5. Or if you want, if you change to a j, x to the j, and this starts at 5. So in other words, it's x to the 5th plus x to the 6th plus x to the 7th, etc., etc. Okay, so that's the last problem we did yesterday. And now here's our next goal. So now we want to come up with a power series. So what we need to do is find a power series centered at 0 for 1 over 1 minus 2x. Okay, and so how do we do this? Well, see, here's the thing. You need to look at the one we know, which is this one over here, and see how this one and the one we requested are similar or different. And what you can tell is that this one has x over here and this one has 2x. So it would be great if we could change the x for a 2x. And that's exactly what we can do. So the way we recommend is that to do any of these, one easy way to manage it is to rewrite the geometric series, but change the variable. Change it to something like y. So for example, so let's write 1 over 1 minus y as this one, y to the k from 0 to infinity. Okay, so this is the same one. I just changed the letter x to a letter y, and you'll see in a moment why. Because this is what we want. I have this 2x, and I would like this 2x to take the place of y. And can I do it? Yes, I can. It was precisely the previous theorem that we showed last time, theorem 1.11.4. It tells you that you can actually substitute whatever you want in here, whatever power of x or power of x times a constant. So in this case, we can set y to be 2x. And then what do we get? We get 1 over 1 minus 2x equals 2x to the k, which you can simplify a little bit as 2 to the k, x to the k. So that's our new power series. So this one is 1 plus 2x plus 2 squared x squared plus 2 cubed x cubed, etc. All right. Now, what about the interval of convergence? What is the interval of convergence? Well, the question is also easy to answer. The only thing we need to remember is what was the interval of convergence of the original one that we started with, right? That one over there had as an interval of convergence absolute value of y less than 1. In other words, from -1 to 1. So all we need to do now is remember that the value of y is 2x. So let's write it here. Original had interval of convergence y less than 1 in absolute value. That is from -1 to 1. So all you need to do to find the new one is plug what your y is and figure out what is the new one for x. So if you take this expression and you put it in here, so for the new one, we pick 2x less than 1 because y equals 2x. And then that's the same as 2 absolute value of x is less than 1, or absolute value of x is less than 1/2. So the new interval of convergence for this one is from -1/2 to 1/2. So, or like this, -1/2 to 1/2. Okay? Questions? All right, let's do another one. So this next one is now for the series, the function 1/1 plus x squared. Let's see if we can do it in a similar way. Here we go. So same question. Find a power series centered at 0 for (1/1 plus x squared). Okay. So again, all of these, the clue that we were given is that all of these come from the geometric series. So again, let's start by writing down the geometric series. So our geometric series with y looks like this. 1/1 minus y is y to the k, the series from 0 to infinity. And we know that this expression is good for y less than 1. Okay. Now, same as before. What can we use? What y should we use so that this expression becomes this one? Yes, so Michael said x squared. Almost, it's not quite x squared. Yeah, Alexander is right. Negative x squared, right? We should use negative x squared. So answer, y equals negative x squared. Right, and then we just plug it in, and what do we get? We get 1/1 minus negative x squared. The negative will, with this other minus, will become the positive that we want. And so this is 1/1 plus x squared. And all we need to do is, instead of y, we're putting negative x squared to the power k. We can simplify it, and it will look like -1 to the k x to the 2k, right? This is interesting, so let's write a few of the terms. So it starts at 0, so it's 1, then it's negative minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus x to the 10th, and it keeps going on like that. It alternates signs, and it goes with the even exponents, all right? Very good. Now, what about its interval of convergence? Well, same thing, right? So we simply use what y is, and we plug it into the condition we have for y. So for the interval of convergence, we know it should be negative x squared in absolute value less than 1, because that's what the y is. And the negative sign with the absolute value is killed, so this is just the same as x squared less than 1. And x squared less than 1 is the same as absolute value of x less than 1. So it happened to be the same by accident, right? Just because we just use, just because the square root of 1 is 1, we got the same one. So it's, the interval is from -1 to 1, just as the original geometric series. All right, questions? Okay. Now, there are more of these we can do, but now I want to talk about another property, another type of thing you can do. And this one is that we can also, it turns out that we can take the derivative or integrate a power series. And the corresponding one that you get is also if the original one was convergent, then the derivative one will be convergent. If the original one was convergent and you integrate, then the other one will be convergent as well on the interval of convergence, except maybe at the endpoints. So at the endpoints, the behavior may change. At the endpoints, it may go from convergent to divergent, or from divergent to convergent. All possibilities are available, all right? So again, inside the interval of convergence, when you take the derivative, it will still be convergent, or if you integrate, it will still be convergent. So I'll show it to you from the book. See, so it's a bit complicated, but let's see. All right, let me show it to you. Right here. All right, so this is the theorem we want to talk about. Good. All right, so here's what we have. We have a regular power series centered at A, and we know that it converges inside this. This is the radius of convergence R. So inside the interval of convergence, it represents some function f on that interval. If that happens, then you can take the derivative. And by taking the derivative, what we mean is, well, you can take the derivative at each of the pieces, right? Now, how do we take the derivative of something like this? Well, it's like a polynomial, right? So it's easy. The k comes down, k times ck, and it's right here, k times ck, and then you subtract 1 to the exponent, which is what you have here. And so you can take the derivative term by term, and by doing so, you're going to find the derivative of the original function. Beautiful, huh? So it's like a different way of taking derivatives or integrating. And we can also do the same thing for integrating. So we can integrate, finding the antiderivative of the function f, or the improper integral. And we can do that by doing the antiderivative of each of the terms, right? So how do we take the antiderivative of this over here? This is just a constant. We don't do anything to it. And in this part over here, we add 1 to the exponent. So it becomes k plus 1. You can see it here. And then you divide by that new exponent. And don't forget that at the end, you need to add a constant, right? Plus c. And this new thing will be convergent in the same interval between x minus a and r. All right? So it's a great theorem, and it's a theorem that allows you to find new formulas of power series from ones that you knew before. And as usual, a great point to start is with the geometric one. All right? So for example, to begin with, let's see what will happen if we take the derivative or if we integrate the geometric power series. All right, so let's do that. Put the book away for a moment. And okay, so this is example 4. Okay, example 4. And what we're gonna do is we're gonna start with the geometric series 1 over 1 minus x, and we're gonna differentiate and integrate to figure out what new function, what new expressions and power series we obtain. So example 4, it says we start with f of x equals 1 over 1 minus x. This is this one, x to the k. So that's 1 plus x squared plus x cubed, etc. And this is good for x less than 1. All right, and then for part A is what would happen if we take the derivatives? What do we obtain? So, well, we're gonna obtain f prime. What is the derivative of 1 over 1 minus x? Well, that's like taking the derivative of 1 minus x to the power negative 1. Right? And that's easy. The negative 1 comes down. So it's minus 1 minus x to the power negative 2 times the derivative of the inner function, which is another negative 1. So this negative cancels, that's negative. So it's simply 1 over 1 minus x squared. Right? That's just taking the derivative. So that's okay. That's nothing fancy. The new thing is that this function actually now has a power series centered at 0, which corresponds to taking the derivative of the original power series. So what we know is that this f prime, which is 1 over 1 minus x squared, is actually now what happens when you take the derivatives term by term, right? So that would be k x to the power k minus 1. And we can start at 1 because when you start at 0, you get 0. So that one cancels, right? Now, as we usually say, if it bothers you that it says k minus 1, do a j substitution. So choose j to be k minus 1. And then this becomes j plus 1 times x to the j from this time starting at 0 and going to infinity. So in other words, this one is, it's right here, is 1 plus 2x plus 3x squared plus 4x cubed, etc. Right? So these are the numbers when you take the derivatives of these terms, right? Look, the derivative of 1, nothing. The derivative of x, 1. The derivative of x squared, 2x. The derivative of x cubed, 3x squared, and so on. Okay? Is that clear? Yeah, so we found a new one, a new power series that we didn't know before. This expression 1 plus 2x plus 3x squared plus 4x cubed. When we do that one, we get 1 over 1 minus x parentheses squared, right? And when is this valid? Well, we don't know for sure the interval of convergence, but we do know that the radius of convergence stays the same. So the radius of convergence for this one was 1. So here, r is 1. So then here, r is 1 as well. Now, what about the endpoints? Well, we don't know. The endpoints may or may not work. The endpoints may or may not be convergent. In this case, both of them are not. I'm not gonna do it right here because we have to do more things, but in this case, the endpoints don't work. Here, both endpoints are divergent. It's kind of easy to do if you think about it. For example, one of the endpoints is 1. So when you put 1 here, you get 1 plus 2 plus 3 plus 4. That's obviously divergent. And the other is -1, which will also is not approaching 0. So it's also going to be divergent. So it's not that hard. But I want to do the other one. I want to do what happens when we take the when we integrate term by term. All right. So part B. What happens now when we integrate term by term? So what happens when we do the integral of f? So it will be the integral of dx over 1 minus x. And what is that one? Maybe better if you look at it like this. So what is it? Yeah, ln, right. Who said ln? You, yes, very nice. So the negative sign stays there, and then it's ln of x minus 1, right, plus c. Good job. Tyler, Daniel, and Nancy. Thank you. Yes, so that's what we have. I mean, we don't need to put the c because we're going to include the c on the other side of the inequality, right, of when we integrate each one of the terms. So this is what we have. We have that, so the negative ln of x minus 1 in absolute value, that is the integral of f of x dx. And that's the same as if we integrate each one of these terms, right? But these are easy. I mean, how do you integrate x to the k? You add 1 to the exponent, and then you divide by that new exponent, k plus 1, right? And again, if you want to make it so that it doesn't have exponent k plus 1 but exponent j, you can do a j substitution. So make j k plus 1. And this is now x to the j divided by j, and where j starts at 1 and it goes to the infinity. Oh, plus c. Okay, so let's write it down over here. Negative ln of x minus 1 will be, what is it? The sum from 1 to infinity of x to the j over j plus c. So this is like c plus x squared over 2 plus x cubed over 3 plus x to the 4 over 4 plus x to the 5 over 5, etc. Now, it turns out that we can actually find out what the c is, right? All we need to do is plug a specific number here, a number that will work. And usually the one that works beautifully is the center, right? All of these power series that we have been doing started from the geometric series, and that geometric series was centered at 0. So what happens when we plug 0? On the left-hand side, we get negative ln of absolute value of -1, right? And on the right-hand side, we get c plus 0 plus 0 squared over 2 plus 0 cubed over 3, etc. They're all zeros, right? All of this is 0. So this is c as the only thing that survives. And this is ln of 1. What is ln of 1? 0. That's right. So we got the value of c, right? So z is 0. Okay, so then we can rewrite this one here is what we have. We have ln, negative ln of x minus 1 is actually x plus x squared over 2 plus x cubed over 3 plus x to the 4 over 4 plus x to the 5th over 5, etc. All right, questions so far? Okay, now what about the interval of convergence or the radius of convergence? Well, for this one, so the same thing, right? What the radius of convergence for the original one was 1. For the original geometric series. So here r equals 1 as well. Well, what about the endpoints? Let's check the endpoints for this one. All right, what the two endpoints are x equals -1 and x equals 1. So let me start with 1. If x equals 1, then what is x plus x squared over 2 plus x cubed over 3 plus x to the 4 over 4? Well, that's just 1 over k, right? And what do we know about this series? Yes, it diverges, right? It's by p test. Thank you, Michael. Diverges by p series. So 1 is not convergent. But what about -1? Well, for -1, our series x to the k over k becomes -1 to the k over k, which is 1 minus a half plus a third minus a fourth. And this was our first example of the alternating series test, if you remember, right? This is here, this one converges by alternating series test. Why? Because the limit of 1 over k is 0. And 1 over k plus 1 is smaller than 1 over k. So these are the two properties. So this one is convergent. All right, so then the interval of convergence of this one, of this new power series, is from -1 to 1, where we include -1 and we don't include 1. All right, now notice this is an example where the original one, see the original one, the geometric series was not convergent at -1. But once we integrate it, the new one is convergent at -1. So the behavior at the endpoint changed. And that can happen, all right? Now, the other beautiful thing here is that, I mean, the theorem only tells you that this equality, this one over here, this equality only happens inside the interval of convergence. It doesn't tell you what happens at the endpoints. So, in other words, we saw that this one converges at -1, but we don't know if it equals this one. It in fact does. So by continuity. So we're not going to argue it right now, but this is a beautiful, beautiful result on its own that maybe you would like to know. So we know it's convergent at -1. So what happens when you plug -1 in here? What happens is you get negative ln of -1 minus 1 in absolute value equals -1 plus 1/2 minus 1/3 plus 1/4 minus 1/5 plus etc. Right? And this number is 2. So negative ln 2 is -1 plus 1/2 minus 1/3 plus 1/4 minus a fifth, etc. Beautiful, right? And also, even better, if you multiply by -1, you get an even prettier one. So if you multiply by -1, then it looks like this. It looks like ln2 is 1 minus a half plus a third minus a fourth plus 1/5 minus a sixth, etc. So look at that. We just discovered what the alternating harmonic series converges to. It converges to ln of 2, believe it or not, right? It seems like a weird number for it to be convergent to, but that's the answer. It's ln of 2. That's the value that it converges to. All right. Questions? All right. So there's more here. And this is kind of challenging. This next one over here will be a more challenging problem. So now is, for these ones, you need to be really, really creative. So this is example 5. And what we want to do is, this time I'm gonna give you a function, and you need to be creative enough to come up with a power series. All right. So this time I'm gonna show you a function. Like imagine that I had told you ln of x minus 1, and you need to figure out how you can get ln of x minus 1 out of the power series you already know. Okay. So again, I agree. This is challenging. This requires creativity. You need to figure out how you can come up with the right function. Okay. So we'll start with part A. For part A, here's the one we want to do. We want to do arctangent or inverse tangent. All right. Let's see if we can come up with inverse tangent. So find a power series for inverse tangent. I like to call it arctangent. Centered at 0. All right, how do we do that? Well, what do we have, right? What properties do we know about arctangent? How can we relate it to a power series that we already know? Okay, and we don't know much. We really know the geometric series, which is the one we just did. So let's try. So here's something that is nice about arctangent function. What is the derivative of arctangent? Yes, Daniel, you're right about that. So it's 1 over x squared plus 1. Actually, yeah. Or let me write it like this: 1 plus x squared. Now, does that remind you of something? Do we know the power series of this guy? We do, right? Here's a trip down memory lane, right? We did this one before, right? The way we did it was by starting with the geometric series. And then what we did is we changed y to negative x squared, put it in here, and voila, here's our power series for 1 over 1 plus x squared. Now, all right, so let me write that down. Let me bring that in here. So we already know that 1 over 1 plus x squared is actually the same as this one. From 0 to infinity, negative 1 to the k, x to the 2k. So in other words, this is 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th. Right? Okay. So now the next question is, how do we combine these two pieces of information, these two clues, to get the one we want? We want one for arctangent. We know the derivative of arctangent is this. And we already know a power series for that. Now, how do we get a power series for arctangent, for this one over here? How do we do it? Yes, Jose, you're right about that. We integrate, right? So if we know that the derivative of arctangent is this one, then to recover, to start from this one and get that one, we reverse the derivative. And how do we reverse the derivative? We integrate, right? So that's exactly what we're gonna do. So we're gonna start from this one and we're gonna integrate. All right, let's see if we can do it. So the integral of 1 over 1 plus x squared will be if we integrate this term by term, right? This time I'll actually do it right here. So what's the integral of 1? X. What's the integral of negative x squared? It's negative x cubed over 3. What is the integral of x to the 4th? Is x to the 5th over 5. And this one is x to the 7 over 7. And that's x to the 9 over 9. And it keeps alternating signs, right? Look at that beautiful pattern. These are the odd numbers, 3, 5, 7, 9, right? And on this side, what is the integral of 1 plus x squared? Well, it's exactly what we want, right? Is arctangent or inverse tangent. And don't forget to put the c, right? We need to put the c at the very end. And I would like to discover what the c is. So to discover what the c is, we're gonna plug 0 as usual. So plug x equals 0. So what is inverse tangent of 0? That's 0, because tangent of 0 is 0. And then on this side, when we plug 0, we get 0 minus 0 cubed over 3 plus 0 to the 5 over 5, etc., plus c. So all of this is just 0. So that means that c is 0. And what is then our new power series? Here it is. Our power series for inverse tangent is this one. X minus x cubed over 3 plus x to the 5 over 5 minus x to the 7 over 7 plus x to the 9 over 9 minus x to 11 over 11, etc. Here's how we can write it with the sigma notation. This will be negative 1 to the k, x to the 2k plus 1 divided by 2k plus 1, starting at 0 and going all the way to infinity. All right? Beautiful formula, right? Beautiful, nice pattern with the odd numbers. Now the question is, where is this formula valid, right? What is the interval of convergence? And for that, we need to backtrack, right? So backtrack. So which one did we use? We used this one. What was the interval of convergence for this one? Well, from negative 1 to 1, right? If we look back, let me backtrack even more. When we did it, we asked over here, what's the interval of convergence? And we said that we plugged negative x squared. So it was from negative 1 to 1, the interval of convergence. All right, so back to the one we have. So this one is good for x between negative 1 and 1. That means the radius is 1. Then from here to here, we integrate it. When you integrate, the radius is the same. So R equals 1 as well. But we don't know anything about the endpoints. Okay, so for this one, we know it's true. So this one over here is correct or convergent if absolute value of X is less than 1. We don't know about the endpoints. We would need to check them one by one. All right, now I'm not gonna do it right now, but it turns out here that the endpoints, the one that is 1 is convergent. So I'm not gonna do the details, but X equals 1 is convergent, and X equals -1 is divergent. But I'm not going to show you I mean, you can try to do it. It's not that bad. This one is just the alternating series test. And for this one, you need to be a little creative, but you can, I mean, you can use the integral test, for example, for this other one over here. All right. Okay, so that was difficult, right? I mean, this is a challenging problem. It required us to come up with. You need to remember the right function to begin with, right? So from the geometric, we first plug -x² to get that intermediate one, and then we have to integrate to get the one for arctangent. All right, so we'll do another problem like this. See, this time we're gonna do part B, and for part B, we need to find out a power series, this time for ln of 1 plus x over ln of 1 minus x. Difficult one as well, all right? So let's see. So find a power series centered at 0. Okay, woof, looks tough, right? Now, what can we use? We already have one that is sort of related, right? This sounds familiar to one we did before. Let's check our notes of the ones we worked before. And I see this one. We did this one, right? We did ln of x minus 1 in absolute value. So at least when x minus 1 is positive, when you don't have the absolute value, then it's sort of the same, right? So I guess we can change this to 1 minus x, and that way it's positive, right, in the corresponding range. So we do have one part over here, this part over here at least, right? Now, what else can we do? Well, as usual, if you have a difficult problem, break it down into smaller problems, right? So here, for instance, see, we can use properties of the logarithms, right? What is this by properties of the logarithms? It's a quotient, and the logarithm of a quotient is the difference of the logarithms. So this is the same as ln of 1 plus x minus ln of 1 minus x, right? So that's good, because maybe we can do this one and then that one and then put them together. That's a nice plan to do this difficult problem. So first, let me copy the one we had done before. So we had done before this one over here, negative ln of x minus 1, and this one was x to the k over k. And this one was good for x between -1 and 1. Mhm. Now, I want to get rid of the absolute value. And there's an easy way. Look in here. When this is true, only in this range. And here, if -1 is less than x less than 1, then what happens to x minus 1? Is negative, right? And then what's the absolute value of x minus 1? Because it's a negative number, we should multiply it by minus. So it becomes 1 minus x, right? So then I can change this to minus ln of 1 minus x, this time with no absolute value bar. And this is awesome because look, this one over here is this part. So I already did have this problem, right? It turns out that we had already done half this problem. Now we only need to work with 1 plus x, ln of 1 plus x. All right? Okay. So let's work the other part. So we're gonna leave this pending till we finish the rest of the stuff, and then when we finish this part over here, we'll put them together. All right? So now let's work on ln of 1 plus x. All right. Now let's try to do it in the same way that we did ln of 1 minus x. So, well, what do we know about ln of 1 plus x? Well, what would be its derivative? What is the derivative of ln of 1 plus x? Yes, Daniel, thank you. It is indeed 1 over 1 plus x, right? Okay, so then that's my first question. Can we get a power series for 1 over 1 plus x? Because if we can, then when we get the power series for this one, to get the one we want, we simply reverse the derivative. That is, we integrate, right? Okay, so, and yes, that's the way we're gonna do it. So the answer to this is yes. And the way we're gonna do it is the same as the other one. We're gonna start with 1 over 1, with the geometric one. It's always a geometric or go-to guy, right? We start with 1 over 1 minus y. That's y to the k from 0 to infinity. And what y should we use so that we get 1 over 1 plus x? Negative x, you're right, Harnit and Gerardo and Daniel. Yes, let's pick negative x. So we plug it in here, and then we get 1 over 1 minus negative x. That's 1 over 1 plus x, just what we have, what we want. And that's going to be negative x to the k. So that's the same as negative 1 to the k, x to the k. All right, so that's half of it. So we already have this one. Now, and when we do this, the radius of convergence, let's figure it out. So this one was good for y less than 1. Y less than 1. And then to figure out the new one, this will be negative x less than 1, which is the same. You know, the absolute value kills the negative sign, so that's just x less than 1. So we get the same thing. All right. Now, to get ln of 1 plus x, now what we need to do is we need to reverse the derivative, and that means we need to integrate. So we integrate now. So the integral of 1 over 1 plus x, that will be what we want. And now we just need to integrate term by term. And what is that? That's negative 1 to the k, x to the k plus 1 divided by k plus 1 plus c. And if we, again, I don't like it that it has power k plus 1, so I'm going to get j to be k plus 1. So now it's the sum, it's negative 1 to the j minus 1 or j plus 1, doesn't matter. X to the j divided by j from 1 to infinity plus c. All right, awesome. We have the two pieces. This is one of the, so this, can write it here. That's ln of 1 plus x. This, oh, we should probably figure out the c, right? So if we plug 0, if x equals 0, then we get ln of 1, which is 0. And that's gonna be the same as c. So the c is 0 as well for this one. All right, now time to put it all together. So we have this one, and we have this. So well, now we'll put them together to get the one we want. So let's not forget that this is what we really wanted, right? ln of 1 plus x over ln of 1 minus x. I'm going to copy again. All right, now let's copy. What is ln of 1 plus x? And I have it right here. Here's ln of 1 plus x. I'm just going to put it here. So this will be the sum from 1 to infinity, negative 1. Let me change the j to k again, because that's the letter we prefer. All right, that's it. So I just copy this one. Then let's copy the other one. Okay, now note that it already comes with the negative sign, right? It already comes with the negative sign, so I don't need to put another negative sign here. It already has the negative sign. So it's plus x to the k over k. All right? Okay, we're almost done. And where is this true? Well, we can backtrack where everything was true. And so it will be correct between negative 1 and 1. So this one was, we have it right here. This one was good between negative 1 and 1, strict. And this other one, we didn't do it. Maybe we should have done it, right? So this one, we would need to check the endpoints. So for this one, the endpoints are going to work for 1, but not for negative 1. So this one will be good for negative 1. It's not going to work, but 1, it will work. Oops, right here. So it actually is the opposite of this one. Where is the opposite of this one? So for the two of them to work at the same time, we're gonna have to be between negative 1 and 1 strictly. So between negative 1 and 1, strict, both of them. All right. Last step. Michael asked, does it matter that k starts at 1 for the first power series? This one? Both of them start at 1. They should, right? Because if they started at 0, I would be dividing by 0. That would be not right. Okay, so now it'd be nice if we could combine this into a single one, right? And you can, see, you can put these things together so they both have, so it's like, it will be like this. Like that, and then you can factor the things that have in common. So it's the x to the k over k they have in common. And then it's negative 1 to the k plus 1 plus 1. All right? And then observe. See, let's start writing a few of these terms. When k is 1, you get x over 1 times negative 1 to the 1 plus 1, that's to the second power. So that's positive 1. So it's 1 plus 1. Plus, then it's x squared over 2. And then it's negative 1 to the cube. So that's negative 1 plus 1. And that's nice because that becomes 0. Then after that, you get x cubed over 3. And that will be 1 plus 1. Then plus x to the 4 over 4, negative 1 plus 1, plus etc. And I hope you see the pattern that all the even ones are going to be 0. So all the even ones were going to be 0 because you're going to get negative 1 plus 1. So only the odd ones survive, which means we can rewrite that series as x to the 2k plus 1 over 2k plus 1 from 0 to infinity. In other words, this is just x plus x over 3 plus x over 5 plus x over 7, 2x, 2. And I forget, that's 1 plus 1, 1 plus 1 plus 1 plus 1. So it's 2x, 2x over 3, 2x over 5, 2x over 7, etc. All right? And this expression is the same as ln of 1 plus x over 1 minus x. And whenever negative 1 less than x less than 1. All right. Questions? X, something weird here. Hold on a sec. X cubed, x to the 5th, x to the 7th. Thank you. All right. Okay, Nancy is asking, isn't ln of 1 plus x equals minus ln of x minus 1? No, that's not right. So the question is ln of 1 plus x equals minus ln of x minus 1? And no, they're not the same, right? For example, this one is defined at 0, this one is not defined at 0, right? All right, more questions. Okay. Okay. So I agree. These last couple of problems are difficult. They're meant to be. All right. But what we're gonna be doing soon is to find out like a library of power series that we already know, that we're familiar with for many functions. I'm sorry, I was distracted by Nancy still asking about. If you want, Nancy, stay after I wrap up the class, and I can tell you about that. Okay, so we're gonna develop a bunch of power series that we're gonna work with. I mean, we're gonna know quite well. Like we already have some of them. Like you should know the one for ln of 1 plus x, or the one for ln of 1 minus x. Those are basic ones. You should know the one for arctangent. That's another basic one, and that's the reason we actually did it right now. But then the question is, can we work at it the other way around? Let's say we start with a function like we did here, right? Let's say we ask about other functions like sine, cosine, e to the x. And we ask, what is the power series that goes with those? Can we find it? Can we know the formula for that power series? And that's exactly where we're gonna go. So on the next section, we're going to start, it's called Taylor series. And I'm not gonna start it right now because we barely have 2 or 3 minutes left. But with Taylor series, we are going to be able to find out a way to come up with the power series for an arbitrary function, subject to some conditions. So we want, I mean, we still have these restrictions of having the interval of convergence and the radius of convergence. So it's not solve all kind of approach. It's not that we're gonna get a power series that works everywhere, right? But at least on a little interval around our center, we will be able to do it. All right, so that's where we're going with this. I'm gonna stop the session right here. And I'll see you guys tomorrow